In this example, it says that a 0.174 kilogram softball is pitched horizontally at 26.0 meters per second. The ball moves in the opposite direction at 38 meters per second after it's hit by a bat. All right, so first of all, it says the opposite direction, so we're going to say initially that it was moving in the negative direction. So this 26.0 meters per second is actually going to be negative, and then the 38 meters per second is going to be positive. So the first question is find the change in momentum of the ball. So our change in momentum equations is going to be equal to mass times final velocity minus mass times initial velocity. We go ahead and plug in our numbers. So 0.174 times 38 being the final velocity minus 0.174 times negative 26, which was the initial velocity. We get a total change in momentum equal to 11.14 kilograms meters per second. Now the next question says, what is the impulse delivered by the bat? If you remember, impulse is equal to change in momentum. So if we have a change in momentum of 11.14 kilograms meters per second, that means we have an impulse of 11.14. And since we're talking about impulse, we use Newton seconds, which is actually the same units as kilogram meters per second. They turn out to be the same. Next equation, or next part of the question, if the bat and softball are in contact for 0.8 milliseconds, what is the average force that the bat exerts on the ball? Now, if you remember, impulse is not only equal to change momentum, but it's also equal to net force times time. So net force times time is going to be equal to that change in momentum. We know the change in momentum is 11.14 as we figured out before, and we know that the time is going to be 0.8 milliseconds. Now it's important to realize that we're talking about milliseconds. That has to be in base units, so it's actually going to be 0.0008 seconds. All right, so if we take that, in order to find the net force, we divide the change in momentum by time, and we get that 11.14 is going to be divided by 0.00080 seconds, because milliseconds converted to seconds, so we get that our net force is going to be equal to 13,900 newtons. All right, so conservation of momentum. This is the derivation of how we get to conservation momentum. So first of all, we got each car that's applying a force on each other. Car 1 is applying a force on car 2, and car 2 is applying a force back on car 1. In any collision, they apply a force on each other. Now Newton's third law says that these two forces are going to be equal and opposite. So car 1 applies a force on car 2 with the same amount of force that car 2 applies on car 1, but in the opposite direction. Now, because the two are going to be in contact with each other for the same amount of time, car 1 is going to be in contact with car 2 for the same amount of time that car 2 is going to be in contact with car 1. It wouldn't make sense that car 1 is touching car 2 for a longer period of time than 2 is touching 1, so that's the same amount of time for both of them. So we're going to multiply both sides by time. Now what you notice is you got the force times time over here and force times time over here. That's going to be impulse. Impulse equals force times time. So the force 1, 2, that's the force of the first car and the second car, times time is going to be equal to the impulse of the first car. And then the impulse of 2 on 1, so the force back in the other direction multiplied by time is going to be the impulse on the second car. So impulse 1 is going to be equal to the opposite of impulse 2 because of those equal and opposite forces. Well, something we already learned is that impulse is going to be equal to change in momentum. So since the impulse 1 is going to be equal to negative impulse 2, then that means change in momentum 1 is going to be equal to change in momentum 2. Now when we take that to the other side, we get that change in momentum 1 plus change in momentum 2 is going to be equal to 0. So whatever the change in momentum is for the first car plus the change in momentum of the second car is going to give me a total of 0. Now this is assuming there's no outside net force, and the only forces that are acting are the forces that are between these cars. If that's true, then momentum is going to be conserved, meaning the total change is going to be equal to 0. Now a better way to actually write it is going to be that the initial momentum equals the final momentum. It's actually going to be an easier way to think about it, and it's actually making an easier equation. So this is our equation where the first mass times its initial velocity plus the second mass times its initial velocity. That will give us all of the initial momentums. And then we got the first mass times its final velocity plus the second mass times its final velocity. That will give us all the final momentums. So all the initial momentums added together will be equal to all the final momentums added together. So this is going to be our conservation of momentum equation that we're going to use from this point forward. All right, so let's suppose we have a thread that holds a 1.5 kilogram cart and a 4.5 kilogram cart together. After the thread is burned, the compressed spring that's between them pushes the carts apart, giving the 1.5 kilogram cart a speed of 27 centimeters per second to the left. So the question is, what's the final velocity? What's the velocity of the 4.5 kilogram cart? All right, so we're going to use our conservation momentum equation. That's mass 1 times initial velocity 1 plus mass 2 times initial velocity 2 equals mass 1 times final velocity 2, or final velocity 1 plus mass 2 times final velocity 2. Well, first of all, both of them are not moving initially, so the total initial momentum is going to be 0 because 1.5 times 0 plus 4.5 times 0 gives me a total of initial for 0. Afterwards, the 1.5 kilogram mass is moving at 27 centimeters per second. Convert that to meters, and that gives me 0.27. Now, we give it negative because it's moving to the left. We have to incorporate that direction anytime we do conservation momentum because the direction does matter. So with that being said, 1.5 times negative 0.27 gives me negative 0.405. And then the 4.5 times the final velocity 2, and final velocity 2 is what we're looking for. So we take the 0.405 to the other side, make it positive, divide by 4.5, and we get 0.09 meters per second. Now what you notice is your final velocity of the second car is going to be 9 centimeters per second. Now, if you think about conservation of momentum, the momentum initially was 0 because neither car was moving. So the momentum after also has to be 0. So if the first car has a momentum that is 1.5 times 27 centimeters per second, you can figure out mathematically, but think about it like this. If the first mass is 1.5 kilograms, the second mass is 4.5 kilograms, that means the second mass is 3 times the mass of the first one. Well, if it's 3 times the mass and has to have the same momentum, then that means it has to have 1/3 of the velocity. So if the velocity of the first car is 27 centimeters per second, then 1/3 of that will be 9 centimeters per second. So it goes along with what we were talking about with conservation of momentum, that mass times velocity will give you your momentum, and each one's going to be equal and opposite because the total in the initial was 0, so the final also has to be 0, with one being positive and the other being negative. In this example, it says car 1 of mass 6 kilograms is moving at 3.5 meters per second and collides with car 2, the mass of 4 kilograms, that is initially at rest. Car 1 moves off at 0.7 meters per second, the same direction as its initial velocity. All right, so car 1 is initially moving 3.5 meters per second, comes in and hits car 2. Car 1 initially at 3.5 ends at 0.7, so it slows down. Car 2 initially at rest, so it has an initial velocity of 0, and then starts moving off at some velocity that we have to figure out. So we use our conservation of momentum equation. Go ahead and plug in our numbers. The 6 kilograms is the first car times 3.5, and then 4 kilograms times 0, that's the initial velocity of the second car. So 6 times 0.7, that's the final momentum of the first car, and then the final momentum of the second car is 4 times the final velocity. So you put these in your calculator, you get 6 times 3.5 gives me 21, and that's going to give me 0, so I get a total of 21 on the left hand side. And then 6 times 0.7 gives me 4.2. So I'll subtract 4.2 from both sides, it gives me 16.8 on the left hand side. Then I divide by 4, and that gives me a total of 4.2 meters per second for the final velocity. So you can see that the final velocity of the second car is going to increase as the final velocity of the first car decreased from its initial velocity. Now, something you should notice is that the final velocity of the second car has to be greater than 0.7, because if for some reason the first car has a final velocity greater than the second car, then that means the first car would have had to go through the second car, which is not possible. So we were expecting something greater than 0.7 for the final velocity of the second car. In this example, it says that a 35-gram bullet strikes a 5-kilogram stationary piece of lumber and embeds itself in the wood. The piece of lumber and the bullet fly off together at 8.6 meters per second. So what's the original speed of the bullet? So we're trying to look for the initial velocity. All right, so we got our conservation momentum equation. We got all the information given to us. We got 35 grams, which needs to be converted to kilograms. So mass 1 is going to be 0.035. And then the second mass is 5 kilograms. Initially, for the second mass, it has 0 velocity because it's stationary. The final velocity of the second mass is going to be 8.6, and the final velocity of the bullet is going to be 8.6. So we'll go ahead and plug in the information that we know. We know that 0.035 is going to be the mass of the bullet times its initial velocity, which is going to be our unknown, plus 5 times 0. That's the initial velocity of the piece of lumber. So that's going to be 0. and then 0.035 times 8.6 and plus 5 times 8.6, because the final velocity of both of them when they stick together is going to be the same. Now, something to keep in mind here is I get a lot of people who say, well, this bullet stops when it hits the piece of lumber. Actually, it doesn't. When the two stick together, that means they're moving together, so you have to include the bullet with its momentum as it's moving forward. All right, so you punch this in your calculator, you get 0.035 times 8.6, that gives you 0.301, and then 5 times 8.6 gives me 43. Then we add those together, we get 43.301. Then we divide by 0.035, get our initial velocity is 1,240 meters per second.